Okay, so why is this idea of spectra, why is it important? Why is it so exciting? Well, it allows us to modify Rutherford's model to kind of fix. It allows us to think about how the model should actually look, right? It allows us to develop a new model discussed by Niels Bohr. And Niels Bohr it's the model that we jump to whenever we talk about chemistry or physics. It's the simplest one to think of. It just makes sense when we think of an atom. It just makes sense. It describes a lot of the things that we see around us in everyday life, right? There are some limitations, right? It still doesn't explain why electrons, as they move around in circles, don't emit EMR. He just says it doesn't, right? As long as it's within those energy shells. But that's okay, right? We'll fix that model as we get to it. That's probably what he was thinking. He's like, yeah, as long as they're there, it just breaks the rules of physics. Someone else will fix that problem for me. And someone does, that's true. De Broglie comes along, another scientist we talked about in a previous course, or a previous chapter, sorry. He comes and fixes it with his wave models of matter, where fast-moving electrons behave as if they're waves. And waves have different properties than moving particles. They don't accelerate. They're just there. They're standing waves. They're just there. So if they don't accelerate, technically, then they don't release particles or release spectra or energy. Right? It does. His model is now a pretty accepted model, which is kind of nice. Okay. The important part of the spectra, and the next couple of slides just talk about how do we use these spectra to help us figure out things. I talked about that in that previous video, how we could pass continuous light through these gases and determine what the gases are made up by, what do they absorb. Or we can excite those gases and figure out, oh, what are they releasing? We look at the fingerprint of the atoms that are within them. We can also look at Doppler effect and the red shifting as objects are moving away from us or moving towards us. The whole spectrum would just kind of shift side to side. And you're thinking, why would that be? Because they're moving away from us. It's caused by the Doppler effect. It's a cool video if you're thinking about watching a video. The 60-second video or 60 symbol, video about redshift is pretty cool. It's not important for our class, so not too worried about that. So the Bohr model is trying to fix a couple of problems, right? So in the first model, we talked about how chemistry was used to help us discuss those first models. In the third model, we brought up the planetary model, where these electrons are moving around this nucleus. Definitely not drawn to scale here, this horrible picture. I should get rid of it. Where we have all these protons and neutrons in the middle, and we have these electrons whizzling around in all sorts of different places, right? They're not in shells. They're just like planets. They could be anywhere, orbiting at any distance, right? Just whizzing around like crazy. Yeah. But according to Maxwell, those accelerated charges, those electrons should be emitting EMR, and they should just collapse and disappear. Atoms should just not be bonded to other atoms. It just gets a little tricky. So this is obviously not true. So Bohr just proposed in 1915. You remember when Rutherford made his model was 1911. So that was in 4 years. They had to change his model really quickly. He probably realized quickly that, yeah, we're going to have to change it, but change it to what? So Bohr comes along and says, as long as those electrons are within a very specific orbitals, these energy shells, then they're just not going to give off the energy. And they only give off the energy if they move from one shell to another. And they can only exist, and this is the key part to this, they can only exist in those shells. An electron can't be halfway between a shell. That's going to be very key. Okay? Yeah, so to be one of these shells, it must possess the energy required for that shell, right? You can't be halfway. It's like a bookshelf. You can't be halfway up a shelf. If you're halfway up the shelf, you just drop back down to the shelf that you were before. And there's other weird things about this model where, say you move a book from one shelf past another shelf, but you're not quite at that shelf, and you let go of that book. You think it would just go down to the next shelf down, but it actually go all the way down to where it was before. If it doesn't have enough energy to get precisely to the next shelf, it drops all the way back down to where it was. It's a very strange analogy. Okay. Yeah, so let's look at some of these demonstrations here. Okay, pull this over here. Can I zoom in? Probably good. Oh, I can't. Why doesn't let me zoom in? Okay, this looks, it's pretty big as is. Okay, so here is our atom. It's actually looking pretty laggy, so let me just see if I can refresh it. Okay, so here I think I fixed it. Still looks a little bit laggy, but that's okay. But we're getting the gist of it. So obviously it's not drawn to scale. Here's the little spectrometer down here, so I can increase the speed of this. So they're passing a bunch of photons in here. So this is the somewhere down here below this device here is something that's producing a nice continuous spectrum, white light. All these little photons, different wavelengths going along. Some of the photons you can see as it goes in, some of the photons get shot out. There's a photon that got shot out that direction there. They come out, and then they get kind of read onto this spectrometer here. So a bunch of UV light is being spit out. Oh, I think there's one little purple one there that got spit out. Oh, there's a red one over there. And there's an infrared dot over here. So every time you see one that gets spit out in a different direction, this thing reads it. A lot more ultraviolet than others. Okay? But if I let that thing run for a while, these little lines here will get taller with photon readings as you go. And this is as fast as it goes, though. Okay, so let's look at the predictions here. So if this was the billiard ball model, right? So back to Dalton here. So if I were to run this, this is what you would expect to happen if the billiard ball model is true. Well, all the light would just reflect off it. That's it. All the light. So just they bounce right off it because it's a solid, right? So most things, if it's a solid, light will just reflect off that surface and nothing would get through. Okay? So it would technically block all the light in the behind it. So if this was just a gold foil, nothing would get through. Nothing, you would not detect anything on the other side. I mean, that's not true because we see nowadays that there's stuff on the other side as well. Now here's another one. Okay, so it hits that electron, the electron absorbs it, it jiggles around, and then it shoots off a photon. And you notice that it's always absorbing all of the electrons. So every time it absorbs it, so this one it gets absorbed to yellow, and then it spits out. And these little purple guys, these are ultraviolet. The purple ones are ultraviolet. So it's always spitting out ultraviolet. But that's not true. Like this is not what the spectrometer reading of a hydrogen gas looks like. It has other lines in it. As we saw in the experiment, it showed a little bit of purple, or like one blue, there's a red, and there's some infrared, but you notice this is all the same. Okay, so this model didn't work. Now, watch this one very carefully for the classical model. This is Rutherford's. Boom. I'll go back to it. Watch that electron. There's an electron that kind of spins around there. Done. Right? Obviously, that doesn't happen, so this classical model's wrong. So they're saying that the electron should just keep on spinning around, losing energy as it goes, and eventually collapse. I don't know about the kaboom part, but it's a bit dramatic. Now here's the Bohr model. Okay. So we're going to watch this for a little bit. Once in a while, you can see the electron there that's orbiting. So this down here is called the ground state. That's where the electron wants to be. Once in a while, you can see the electron jump to other energy levels. Okay, so here it is. It's going to get hit by this ultraviolet. Now it's here on the second, or 1, 2, 3, the third level there. It goes down to the second level, down to this level. And every time it jumps down, it releases a photon in a random direction, but then it gets registered down here. You can see now this is kind of matching what we saw before. Here you got some red, you got some ultraviolet, we got ultraviolet over here, sorry, you got some blue, you got some purple in there too. Right, so it's matching more closely what it should be. Now de Broglie fixes some problems. De Broglie does, we'll talk about de Broglie later on, but you can see the model here. The electron is now a wave, but it follows the same idea. It gets hit by certain light, changes energy shell, and then it collapses down back to the ground state. So you'll see here it get hit again. So now it goes up to the energy shell. and then it goes down, and down again. There you go. And as it does, it releases light. Extraordinary does a cloud thing. It's hard to see the cloud in this one, but when it's excited, the cloud changes shape, and when it gets unexcited, it releases a photon. You can see a photon there fly off. So let's go back to the Bohr model. Okay, show the energy levels. So this is just showing energy level 1. This is our ground state. Every time it gets excited, you can see it go up, and every time it goes down, you can see. And the color of that line tells us the color of the photon that's releasing as well. So there's a ultraviolet, and then ultraviolet as it goes down. Okay, so what I'm going to do is I'm going to change this a little bit. Okay, so I'm just going to run this with red light. Now, red light, what we know about red light, long wavelengths, low energy. Now, the energy difference from here to the second shell, that's the closest shell here, is quite a big jump. And we'll talk about that later on. This number is like in the 10 electron volts or something. And red light is not 10 electron volts. Now, the lines that this could absorb, because it can absorb more than just the ultraviolet, but the first line that absorbs is way over here. Right there. So, sorry, I'll go back to that. But 121, 123, right about there. Let's see if it gets it. Now it's got a hit. Oh, it's supposed to be absorbing here. Come on. Right there. Come on. It's not being very nice. It's supposed to absorb that. Let me just fix this and we'll be right back. Okay, so I think I fixed it here. So we're at 121 nanometers. You can see it's highlighted here. That's just enough energy to get that electron from this shell to this shell above it. That distance there is the energy of 121 nanometer wavelength photon. You can just change that using hc over lambda. You can find out how much energy that actually is. Okay. Now, if I wanted to go to a higher level, I would have to go from 1 to 3. Now, the weird thing is that you think, oh, if this is enough energy to get me to level 2, then you think, I don't know, let's say 119, 113. You'd think 113 would be enough energy too, right? Like a 113 nanometer wavelength light going through this thing right now, that's higher energy, so that should get me to level 2. But it's not going up to level 2. Only the 121 did. Right, let's see, run the 121 here. There, so the 121. Those photons get me up to the right level. And every time it jumps down, you can see as it jumps down, it releases the same energy level, so it's always going to be the same right here. Jumps up and then jumps down. So this energy is not, for some reason, this energy at 113 is not enough. Or is it? Well, it's more than enough to get to level 2. So it lands somewhere in here, in between 2 and 3. But because it's not enough to get me precisely to 3 or 2, for some reason the electron just knows, okay, you're not going to get me to where I need to go, so you're not useful. And if you're not useful, I'm just going to ignore you and just let you go on through and do nothing. It's pretty interesting that an electron would know that it needs a very specific photon to get to where it needs to get to. It's a very interesting condition, problem, or characteristic of the electron. If it's not enough or too much, it's not going to use it. It has to be exactly the right amount. So if I keep on going a little bit more, I can go right to the next one here. See, right here, 105. Oh, 105 is too high. Let me see if we can get to the next one here. 103? Let's see where does that go? Okay, 103 gets me to level 3 here. Okay, so 103 is just enough to get me to level 3. Now the fun thing about this, now cool. So you can see in this demonstration, it goes up there to level 3. That's just enough, but it doesn't always have to go right back down to number 1. It could take multiple steps going down. So this is how we can release the red light that you see in the spectrometer, because sure, it's going to absorb ultraviolet light, but it can release red light, right? Now, this is not showing all the different kind of fun characteristics that you can get. Like if a photon were to hit it while it was in level 2, then it could bounce it back. It could bounce it up a little bit more too. This one's a bit harder to see. You can't really see that jump here because all I'm doing is showing one type of light coming through. So every once in a while you can see that jump down. Now, I can move this slightly over. Now all these are really, really close to each other, so I can go to 100. I don't know where did 100 go. Where does 100 go? Let's see. 100. 100 doesn't pop us anywhere. I gotta make sure we're to the right spot. Where's 97 go? Okay, 97 gets us to, let me just wait till it gets to the ground state. There, where 97 gets us to 4. Okay, so as it goes from up to 4, it can jump down 1. So that's probably infrared, that little dot right there. Jump down again. So let's see if we can jump down. If we go jump down to level 2, we can get like a blue light out of this. You can see a blue light was there already. You can go faster. There's a red one there. Ultraviolet one. You can watch this for a long time. It's kind of fun. Okay, I go even more. Looks like here I think I can go up to 192. Is that enough to get me to the very top? Not. Oh, it's not letting me get to the top. It's highlighted here, but it's not letting me get there. Oh, I can get up to 5, I think, with this 195 here. Yeah, it gives me level 5. Okay, we'll talk about this as well later on, where if I can get right to the very top, what's called N infinity, you know the numbers go from 1 to 6. If I get to N infinity, I can ionize this atom. And that's called ionizing radiation. That's the bad type of radiation. We don't want to ionize atoms. But if they do, the electron would just be ejected from the atom itself. So I can get that much energy, then I can do that. So you can see this ultraviolet's getting pretty close to being ionizing energy. I can get that pretty close to the outside edge. But if I go into the higher band here, with the higher frequency stuff, the lower wavelengths, I can ionize this and cause some damage. That's why ultraviolet damages your skin. And that's why gamma radiation and X-rays are also damaging, because they ionize atoms, because they have enough energy to strip electrons away from the atom itself. Okay, so the one takeaway from this, and you need to know this, is that you need the precise amount of energy in a photon to get you to the next level. Okay? If it's a little bit more or a little bit less, it's not going to move the electron. Right? So that's the takeaway from this one. Okay, I have another demonstration here. I'm going to just close this one down, because I don't need to come back to this, do I? No, I don't. Let's get rid of that one. Another one. Where'd that one go? I seem to have lost it. I'm losing my mind here. It says right there. Where is it? Oh, it's right here. Okay, I found it. Okay. This one here shows it a little bit differently. So this is the same idea. This is, I think it's helium. Well, it's neon, right? Multiple atoms. Can I change it to, that's just one atom. Okay, so this is a neon tube. But the idea of this one, it's shooting electrons. So electrons can excite an atom too. So you don't necessarily have to shoot photons that have energy. The photons would excite the gas and be absorbed or then release that light. I can excite it using electrons. So I can fire an electron off this thing, and then it's going to hit this gas here, and you can see on the other side. If the electron has enough energy, it will pass off the energy that the atom could use to get me to the next energy, and then keep the rest. It's not like the photon. Remember, the photon needs to have the exact amount of energy, or it's just not going to be used at all. Right? But in this case, as long as you have enough energy, let me just move this on this side here. As long as you have enough energy, the electron is going to be used. In this case right now, this electron, because I just moved it a little bit closer, you can see the energy. So as I If I move it further away over here, it gives the electron more time to speed up. As it's closer, the electron that shoots off here, by the time it gets here, it's not going fast enough. So you can see from this red line here how much energy it has. So this electron, by the time it gets to here, doesn't have enough energy to get it to the next level. So at least it's smart enough there. It won't even collide with it. It'll just pass on through. It just passes on through, and then it's not used, right? Same thing with the photon, right? If it's not enough energy, it won't do that. Now, if it has enough energy, so right here, I find the electron. Okay, yeah, so it excites this guy, the electron that's in the ground state that's within the atom, gets jumped up. And then when it goes down, it shoots off a photon. Right, the photon, those are those. That photon, there, you can see that photon. Photon goes off there. If I show the spectrometer, I don't know if I can actually see it. Right here. So there's my spectrometer. I can fire this off here. So it shot off a photon. You can see right there, it shot off a photon of ultraviolet light. Because that distance, remember that distance was an ultraviolet light distance. Okay. Oh yeah, this is hydrogen, so this is good. So it's very similar to what we just saw. Now, if this was a photon, this energy of a photon would not be enough to get me to 2 or 3 exactly. And because of that, if this was a photon, the photon would shoot on through and do nothing at all. It would just pass straight on through. It wouldn't give up any of its energy because it's not enough. It's an all or nothing situation for a photon. But because the electron uses classical kinetic energy definitions here, an electron is allowed to give up just a little bit of its energy to get it to the next level. And you can see it slows down. The electron slows down when it gets to the other side. So if I move it down a bit more, I can see the slow down more. There, it slows down, then speeds back up because it's still accelerating this way. So if it has enough, it'll give away most of its energy to get to level 2 and keep the rest as for itself and then pass on through. Right, so even if I get to here, so it got it to 2 and then kept the rest of it. If it can get it to 3, there you go. Let's see if we can get it to 3. There you go. So it got it to 3. So hit it and got it to 3. Sometimes it goes down to 2. Kind of finicky little system here. Yeah, so now I can just shoot a bunch of photons or electrons at it. There you go. Now you can see some cool, interesting things about this is that how do we get those other absorption lines? If it's only absorbing ultraviolet, how do I get other ones? Is that once in a while, if it hits it at just the right place, when the electron on here is in the right spot and gets hit again, it could jump up higher because that electron now has enough energy to get to higher levels because it's starting at a different spot this time. So that's how we're getting more of these lines down here. Pretty cool. I like this thing. So the takeaway from this one, electrons are allowed to give up energy and keep some for themselves to get it to the next level, to get that electron that it collides with to the next level. So it doesn't have to be precise. It just has to be enough to get to me to the level, and I'll keep the rest. Photons have to be precise. They have to be exactly the same, right amount of money. There is a little bit of wiggle room because of Heisenberg's uncertainty principle. There's a little curve and stuff, but it has to be precise enough that to get me to the next level, or it's just not going to be used at all. And that photon's just not going to move. It's not going to go up and then come back down. It's just going to stay where it is. The electron's just going to stay there. So here comes the photon. It just passes straight on through. So that's why, let me just stop this garbage here. Okay. I'll close this down. I might need to come back to that. That's why in our absorption spectrums, I may stop this video soon. Oh, yeah, we're in a long time on this video. That's why in these absorption spectrums, there's not big bands of black lines in here because only the photons that it needs are being absorbed. So these ones are the ones that are being used. These ones here, sure, they have enough energy to get me to this one over here, but it's not exact. So it's not going to be used. So it'll just pass straight on through. And then when they jump back down, they will release that same light. as they go down from one level to another level. That's where these ones come from. So they get excited, and then they come back down. They'll release these different colors of lights. Okay. Go back down to where we were. And we'll probably stop this video. This would be an animation if you're in class, but the animations I saw a lot better. I'll ignore that. Okay, so we'll talk about these Paschen lines and the Balmer lines and the Lyman lines in the next video, and I'll see you then.